All right, cool. Recording in progress.
Yeah, just give me a second to introduce the speakers and then we'll take it away. Right. Right. Hey, everyone. Thanks so much for coming here for probably the inaugural NTNU Julia seminar, hopefully one of many. So I'm Avinash Subramanian. I'm a software engineer at JuliaHub, and we have a few interesting presentations. Chris Rakakis. The first is Fredrik Bagge Carlson, who leads the control team at JuliaHub. And we also have in the afternoon speakers from NTNU and a presentation from Syntef as well. So I'll just let Fredrik take it away then.
All right, cool. Thank you, Avinash. I trust everyone can hear me. If not, then please shout out. Today, we'll talk about a mix of different things that might be interesting for control engineers approaching the Julia programming language. So as Avinash mentioned, I work for JuliaHub. We build a lot of this infrastructure. Here we have a little diagram where in the bottom we have the Julia programming language, on top of which we build everything that we will talk about today. We also have the SciML organization, which Chris is primarily responsible for. So that contains things like differential equation solvers, other equation solvers, DAE, PDE, nonlinear root finding equations, linear systems, and so on. And we have the Julia control organization, which I am responsible for. So that serves as the foundation on top of which we have a modeling language called modeling toolkit. So it's an acausal modeling language. It's similar in spirit to Modelica, if you're familiar with that. And that on top of that, we build a library of different model components. So we have a standard library that is in fact open source. And then we have a number of proprietary model libraries that are industry grade modeling libraries for industry to build and get quickly up to speed with their modeling. So things like HVAC battery and multi-body. And then on top of these modeling libraries, we have a number of capabilities. So for instance, model calibration, model discovery, more advanced control functionalities that we will speak a bit about today, and surrogatization. Today we will speak about the package landscape for the control in Julia. We will look at a little demo of the basic control package. We will look at the demo of the modeling language. If time permits, we will also have a look at the code generation and perhaps the differentiable control design, which is a kind of a hot topic right now. So here is a complicated diagram of the control landscape in Julia. So we start, of course, with in purple here, we have the Julia programming language. Then to the left of the screen, we have in blue the Julia control organization. So under this, you find everything related to classical linear control. And we have a fairly comprehensive coverage of everything you might expect to find in a typical control systems library. So we have the control systems and the control systems base packages. Those implement your typical LQR, Kalman, Bode plots, Nyquist plots, and linear system types that you might find in the control systems toolbox. We will look at how they behave in a demo coming up. We also have a robust control toolbox where you find uncertainty modeling, H-infinity, control design, and this kind of features. You find it in there. We have a system identification package, so that would be your standard linear system identification. Subspace-based methods, prediction error method, estimate transfer functions, and so on. And then in the center of the screen here, we have the SciML organization. This is a vast organization with probably hundreds of packages. But to the control engineer, the packages of primary interest are, of course, the differential equation solvers. And differential equations.jl, the package here, is an umbrella package that underneath has several different differential equation solvers. We also have the modeling language as part of this organization, and the modeling language has an associated standard library that you can build upon. So we will look at these packages today. We also have other organizations that are not part of the JuliaHub umbrella, but of course are usable for anyone that uses the Julia programming language. And one such example is Julia Reach. So they implement methods for reachability analysis. So that's kind of a control analysis method that works for nonlinear systems. So it allows you to say things like, with the given uncertainty, I guarantee that I will never enter an unsafe region, or I guarantee that I will converge to a particular target region, and so on. So these are also kind of interesting new developments that have appeared in the last couple of years. In the bottom of the screen, I show a list of additional interesting things. So the wider ecosystem is actually quite large in Julia. So there are lots of packages for optimal control and trajectory optimization, and I list a few of them here. We also have packages for state estimation, and then we have our own proprietary control extension at JuliaHub that adds things like model predictive controllers and perhaps some more advanced robust control algorithms. You also find a lot of other bits and pieces. So we have a convex optimization package. We have a more general nonlinear optimization package. We have packages for sums of squares programming. So if you have perhaps used JALMIP for this before, we have the equivalent modeling power in sum of squares.jl. If we dive into the demos, we will start looking at a very short demo of the control systems package. So I will switch screen here and shout out if it's too small for you to see. So I'm now in a Pluto notebook. This is a notebook environment similar to Jupyter. There are some differences also. This is a reactive notebook environment. So if I change something in any cell, the entire notebook is automatically recomputed. What I do here is I load a couple of packages. I load the control systems package, plotting, and some linear algebra functionality. So this is just to give you a very first look at how the control systems features look in Julia. Here I create the transfer function. If you're familiar with the control systems library in other languages like Python or MATLAB, it should be familiar. It takes a numerator and denominator polynomial coefficients. I can pass that into the Bode plot command, and then we get the Bode plot. So all of this is standard stuff. The same goes for a Nyquist plot. In the next slide, or in the next cell here, I create an LQR controller. So I first create some state space matrices. I pass them into the state space constructor. I select a penalty matrix here for the LQR controller. The penalty matrix for the control signal is actually set by this slider here. Then I create a state feedback gain. I create a function that computes the state feedback, and I pass that function into the LSIM command. So you might be familiar with LSIM from other toolboxes, and there they typically require you to pass in a vector of control inputs. So we support that also, but here we actually create a function instead. So we implement the state feedback in this function, and we add some disturbance here. If t is larger than 2.5, we add a disturbance with a certain magnitude, and that magnitude is set by this slider as well. So here I demonstrate not only the LQR function, but I also demonstrate these sliders here. So it's actually trivial to make small graphical user interfaces in this notebook environment. And I create these interfaces whenever, actually almost any time I want to design a controller or analyze a problem, and I want to get a feeling for how does this problem depend on a small number of parameters. Then I cook up such an interface so I can get an intuitive feel for it. So I encourage you to try that out if you're interested. All right, I want to show also that we can work with uncertain number types. So here I load a package that provides a particular kind of number. And after I loaded that package, I can create here now, so I have a parameter k, it's 1 plus minus some standard deviation. And that standard deviation is controlled by this slider here. And I do the same for zeta and omega here. And then I pass these numbers into a transfer function. So this transfer function now we see it's printed. The type here is a transfer function. It's continuous time, and it's composed out of particles. So each number is now actually represented as a cloud of 2000 particles. And we see it's printed here. The numerator is 0.89 plus minus some standard deviation here. And if I drag these sliders, we see that the standard deviation here changes. We can plot the density of the numbers probability density of the numbers that I have created. So that's nice, but we can also do computations with this transfer function. So if I ask for the DC gain of this transfer function, we see that I now have a distribution of DC gains. And we can plot the probability density of the DC gain. So we see that I'm slightly uncertain here. Actually, I'm very uncertain about the DC gain. But not only that, let me grab these sliders and bring them with me down. Let's see. I can do things like plot the Bode plot of this transfer function. And we see that now I have some uncertainty in the Bode plot. If I remove the uncertainty in the gain, we see that if I only have uncertainty in the natural frequency, we see that the peak is kind of smeared here. If I have uncertainty in the relative damping, we see that now I am very sure about the DC gain, but I am unsure about the height of this peak. And if I'm just unsure about the gain, we see I just now have a uniform uncertainty along the entire transfer function. So this kind of way of working with the uncertain numbers, it doesn't only work in the control systems package, it works throughout the entire programming language. And it's incredibly useful for engineering style work in general. We're always uncertain about something. We're uncertain about the model, and we're uncertain about the parameters of the model and so on. And this makes it very easy to work with such uncertainty and get kind of a feeling for how does the uncertainty in the input propagate to uncertainty in the output. Where the output can be anything. In this case, it's a Bode plot, but it might be any kind of computation. And we can plot the same thing in a different style here. All right, so this was a very brief overview of how the control systems package look. We will now switch to a little brief demo of how the modeling language looks. So in my presentation here, there is a QR code and there are links. So I will try to share the presentation. But if you go to, there is a course I put up on YouTube. So if you Google my username and Julia course 2022, you will have access to all of these notebooks. You will reach them from there. There is also a video available associated with this notebook if you want to dive into it in a bit more depth. So in this notebook, we will create a simple feedback loop. We will do it using the modeling toolkit language and some of the standard library components. So we have a controller and we have a plant. And if we look inside the plant, we have a DC motor. So here we have a rotating inertia, and we have an electrical part here with a resistor and an inductor, and we have a voltage source. So the voltage source is what we can control here. And the way we build such a model in Modeling Toolkit is that we instantiate the number of components. So here we have some electrical components. We have a ground, voltage, resistor, inductor, and so on, right? And then we form a number of connections. And these connections are acausal, so it doesn't matter which order you list the connected pins here. Modeling Toolkit is an acausal modeling language. So you see that there is an arrow here that shows the definition of a positive current. But there is otherwise no arrow that indicates signal flow. And that's the primary difference between an acausal modeling language and something like Simulink, where everything has an arrow. So we list the connections here, and then we create an ODE system. And then we have created the fundamental model that describes this system here. We can add a PI controller. And the way I do that is I construct here PI controller is a component from the standard library. There is a block library there, and I just pass in some parameters, and the parameters are set by these sliders. So I can now drag these sliders and tune my PI controller. So every time I modify this slider, it performs the simulation and plots that. So using this functionality, I can decide that maybe this is a reasonable tuning there. All right, and now I've used kind of a model to come up to a tuning, and that's very nice and convenient. But we should ensure that we are actually robust with respect to some uncertainty in the model. So very common when you design a controller using a model and you're not actually tuning it on the real system in a lab or in a factory. We want to compute some margins and verify that they are adequate. And there are some built-in features to make that convenient. So in the next cell here, we will compute something called a sensitivity function. If you're familiar with the classical linear controller, we have the definition of the output sensitivity function here. 1/1 plus PC, where P is the plant transfer function and C is the controller transfer function. So we can do that very easily. We just say get sensitivity of the model in a particular signal. And the signal name here is Y. And that gives us the matrices of the state space representation, and we can pass them into the SS command. And I also compute the minimal realization here. And then we get the typical state space system here with A, B, C, and D matrices. We can compute the H infinity norm of that, and then we can plot. So here I plot the sensitivity function in the bottom left, and I indicated the peak value here. So if you're familiar with the classical control, you know that this peak value is associated with a circle here in the Nyquist plot. And that the peak value is the inverse radius of this circle. So we see that this circle just barely touches the Nyquist curve. So we typically want to stay away from the critical point here, right? So, and the further away from the critical point we are, the larger this circle is and the smaller this peak is. So this kind of interface makes it quite convenient to query your nonlinear model for typical linear classical robustness margins. And we can use this to kind of quickly get an intuition for if I change the parameters of my model, if I change the parameters of my controller, what will be the performance using a simulation, and what will be the robustness properties using classical frequency domain techniques. So here I show the most basic frequency domain techniques. We have also other measures from robust control. And if you would like to perform nonlinear robustness analysis, we can do that also using, for instance, reachability analysis. But for the demo today, I think we leave it at this rather simple interface. Hopefully this should be looking quite familiar to all of you. It looks very similar to the interface you might see in either a MATLAB or Python. All right. Moving on. We also have capabilities for estimation and identification. So I mentioned before that control system identification is a package for linear black box identification. It contains all the standard methods you have probably heard about if you have taken a course in system identification. I write here that we have prediction error method, and I say you can easily write this. If you actually follow this link, you will see that we make use of automatic differentiation to derive the gradient of the cost function. So most implementations out there of the prediction error method supports sum of square errors because you get very nice expressions for the gradient. But you can easily request any other cost function. So for instance, you might be interested in optimizing the sum of absolute deviations. And since we make use of automatic differentiation, you get the gradients for free. So you don't have to hard code those by hand. And that's something that goes through the entire Julia programming language, that we can compute gradients, Jacobians, Hessians, and so on for free using automatic differentiation. So that's quite powerful. We also have some standard frequency domain estimation to estimate transfer functions or state space models. We have a library for state estimation, so what you would expect, Kalman filter, EKF, and UKF, and some different formulations of particle filters. There is also the SciML sensitivity package. I think Chris will talk a bit more about these aspects, but that allows you to differentiate through any kind of OD simulation, PD, DAE, and so on, which is quite useful if you want to do some optimization-based workflow, parameter estimation, control design, plant estimation, and so on. We have a library for model predictive control. So Avinash will talk a bit more about this. I will not linger on this slide. there are lots of functionality if you would like to implement this yourself for research purposes. We provide a library in the Julia Sim Control suite of packages, but there are also a couple of community efforts available for model predictive control.jl is a general purpose framework, and contact implicit MPC is for kind of a robotics context. And there are several others here, so this list is far from comprehensive. I have prepared a little demo of differentiable control design. If we have time, and I think we do have some time since I'm speeding through this. So I mentioned before that Julia, the programming language, and that includes then the control system's functionality is fully differentiable. So what that means is that you don't have to write code in a special kind of, imagine PyTorch in Python or TensorFlow or something like that, where you use a special package, like a domain-specific language to implement something that is differentiable. In Julia, everything is differentiable. So you just write Julia code and then you can differentiate through that. And that's extremely powerful for the control engineer. That allows you to do things like system identification using gradient-based methods. Obviously, it allows you to do optimal control and MPC, derive the gradient sessions and Jacobians for free. When I say derive these gradients for free, it obviously costs computation. What it doesn't cost is human labor. You don't need to derive the gradients manually, and you don't need to use finite difference perturbation. You can compute them automatically. You can also do inverse optimal control, which is the little demo I've prepared here. So this notebook is hosted online. I will share it with you. It starts with kind of some exercises actually, and then it moves on to do optimization-based tuning. So we'll tune a PID controller for kind of a double mass system here. So it's two masses or inertias if you want, coupled by a flexible transmission. So we have a spring and a damper here, and we can exert some force or torque on the first mass. So we start by creating that system. It is part of our demo library. It's called double mass model. We have a body plot of it here. So we see we have some resonance here. And here I created a basic tuning by hand. So it's just a very simple PID controller. I pass these parameters into the PID function. I compute the closed loop system using feedback function. I create the sensitivity function, discretize, and perform a step response simulation. And I plot that here. All right, so we see that we have a reasonable robustness margin. We have a low peak in the sensitivity function, but our time response is sluggish, and we want to optimize that. And the way we're going to do that is by just performing optimization. So we're going to perform optimization to optimize this step response performance here, subject to that we don't want to increase this peak in the sensitivity function. So we have a little constraint there. And the way we do that is by loading the optimization package. So optimization.jl is an umbrella package. It contains lots of optimizers underneath the hood. We will use IP-opt for this demo, but there are several others. I create some helper functions. Here we just take the parameters, create the PID controller, and extended gang of 4. So the gang of 4 is a common name for these 4 transfer functions: sensitivity, complementary sensitivity, noise amplification, and attenuation of low disturbances. We have a helper function that performs simulation, and we have a cost function. And finally, we have the constraint function that says that the maximum of the sensitivity function is not allowed to be above a particular value that I have chosen. If we perform that optimization, we see that now the step response is much faster. We see that we respect the constraint on the sensitivity function. So the sensitivity function is the one in blue in the middle plot here, and it's upper bounded by the constraint. And that constraint also corresponds to the circle here in the Nyquist plot. And we see that the optimized loop transfer function is hugging the circle here, and that corresponds to it staying close to the line here for a while. All right, so using automatic differentiation, we were able to tune this PID controller with robustness constraints. But we can make it more interesting. We can do this also for an LQG controller. And if we want to find the penalty matrices for an LQG controller, they are actually being inputted into a Riccati equation solver. We have the Riccati equation in question here. And that gives us the solution to the Riccati equation, this positive semi-definite matrix X that is then used to compute the LQR gain. So can we differentiate through such an equation solver? And the answer is yes, we can. We make use of the implicit function theorem. And in this notebook, it's done manually. But if you ask for the gradient of the Riccati equation, when you use the Julia control systems library, it's done automatically, so you don't actually have to do it yourself. But this is just to show how you can make that happen. So we encode the conditions. That's just the Riccati equation. We encode how we compute the Riccati equation without differentiation. We just call the solver, the RS solver. And then we create the special version of LQR that just calls our implicit Riccati equation solver. And then when we actually solve this problem here, we're looking for the penalty matrices for the LQR cost function. We now obtain optimized penalty matrices. And this is an instance of inverse optimal control. So we are solving a problem to find a cost function. We are actually finding the parameters of the LQR cost function. So that's perhaps a bit different from your traditional optimal control procedure. But we see here again that we are satisfying the sensitivity constraint and we are staying outside the circle here. So this was a kind of a speedy walkthrough of how you can make use of the fact that Julia is fully differentiable to achieve kind of interesting results. So I spoke about inverse optimal control. We actually did the optimization-based tuning of the PID controller as well. Finally, I want to wrap up with some talk about code generation. Can we do code generation? The answer is yes, sometimes. We can do code generation for LTI systems. That's quite straightforward. We can actually produce C code for those. There is also an effort called the static compiler.jl that allows you to statically compile Julia code. So Julia is already a compiled language. Julia writes LLVM code and LLVM writes machine code eventually. So if your target platform has an LLVM compiler, you can actually run Julia code on there. That doesn't mean it's always very simple, but it means that it is possible. And coming up within a year or so is C code generation for arbitrary modeling toolkit code. So hopefully within a year or so, our story on code generation is quite comprehensive. For now, we have a little demo here. So here I load the control systems package and the symbolic control systems package that contains the C code generation. I define a number of variables and then a transfer function. I discretize that and I call the function C code. And I say here that yes, please enable common sub-expression elimination. That gives me a string of C code, and then I just print that string onto a file and I actually compile that. We can look at the C code. It produces something like this. The input to the function is the symbolic variables that I had defined. And then we have the common sub-expressions, and then we compute the output here. So this kind of feature makes it very easy to implement linear control systems. And hopefully within short, we then have this for arbitrary nonlinear modeling toolkit code. But right now, that does not exist. Then we have the static compiler effort that I like to summarize that if you write Julia code similar to if it was C code, meaning that you take care of all your allocations yourself and you free the memory and you don't use garbage collector and you don't have any type instabilities and so on, then you can actually compile Julia code statically. So you get a tiny binary of a couple of kilobytes that you can deploy onto your embedded hardware. And this works for things like Raspberry Pi, and it works for Arduinos even. But it, of course, comes with lots of limitations. So if you're interested in this, please reach out and I can help you get started there. There is a couple of references here to get you started. All right, I want to end with a list of online resources for you to learn more. There is a video series of 10 videos for you to learn how to do control analysis and design in Julia. It's available on YouTube. I encourage you to check out the documentation for control systems and also the one for Julia Sim Control. There is a Julia course that I've held for the Department of Automatic Control in Lund. I've given it 4 or 5 times by now, so it has seen a number of iterations throughout the years. The last version is 2022. And we also have a list of JuliaHub webinars that dive deeper into many of the topics we offer in JuliaHub. And with that, I would like to say thank you. And here are some QR codes if you would like to find the material here. All right, Avinash, I don't know if you have any questions there in the room.
Yeah, that was great. Yeah, we'll switch to the original Zoom link.